quantifier is a way to state that a certain number of elements fulfill some criteria. Open statement is a condition where a sentence contain unknown are not considered to be statements unless the sentence are replaced appropriately. For example, y minus y equal to 8 is an open statement because the value of y is unknown, and as a result, we can state if it is true or false. The uncertainty that we have about y minus y equal to 8 is what makes it an open statement.
There are two types of quantifier, which are existential quantifier and universal quantifier. Existential quantifier will show that a statement is true if and only if there is at least one value of x that makes px true. The quantifier that represent existential quantifier are for some x, for at least one x, and there exists an x such that. As for universal quantifier, the statement is true if and only if at least one value of x is false. The quantifier that shows a universal quantifier are for all x, for any x, for each x, and for every x.
Okay, my name is Nashika binti Syamsuddin, and I will discuss the first question. Let's go to the first A question. It states that determine the true value of each statement. List the indicated universal sets. It's given that the n element of x is 1, 2, and 3, and the inequalities of px is equal to x plus 3 greater than 3. Okay, we go to the first Roman question. The universal quantifier states if px is true for every element x belongs to S. Okay, we already know that the value of x is 1, 2, and 3. Okay, for x is equal to 1, and we substitute 1 into x, and 1 plus 3 is 4. 4 is greater than 3, so the statement is true. For x is equal to 2, and we substitute 2 into x, 2 plus 3 is 5. 5 is greater than 3, so the statement is true. Okay, for x is equal to 3, we substitute 3 into x, so 3 plus 3 is 6. 6 is greater than 3, so the statement is true. So since px is true for all x belongs to S, the statement is true. The existential quantifier asks if there exists at least one x belong to S such that px is true. So from the analysis above, px is true for x equal to 1, 2, and 3. Therefore, at least one x belongs to S satisfies px. So the statement is true. Okay, let's go to the first B question. The question said that determine the true value of the following quantifier statement the natural set of all integers. Explain your answer by giving an example from counter example. We go to the A question. It said that there exists an integer such that both px is true and rx is true. Okay, the first step that we need to do is we need to factorize the equation of px. The equation of px is x squared minus x minus 2 is equal to 0. And then we got this. And then we got the value of x is 2 and value of x is negative 1. Okay, for the step 2 is we need to check the equation of Rx. The equation of Rx is x is greater than or equal to 0. So we substitute the value px just now for x is equal to 2. 2 is greater than 0. So the statement is true. Okay, for x is equal to negative 1. Negative 1 is greater or equal to 0. So the statement is false. Because negative 1 is less than 0. Okay, for step 3 is we need to combine the equation of px and rx. For value of x is equal to 2, px is true and r2 is also true. For the value of x is equal to negative 1, px is true, but r negative 1 is false. Thus, there exists an x, specifically x is equal to 2, that satisfies px and rx. So the statement is true.
Hi, my name is Sarah Najwa with Muhammad Salim. I will continue the presentation about nested quantifiers. Nested quantifiers. A mathematical statement may involve more than one quantifiers. This section offers some example and making some observation on this type of statement. So, I will show you a few questions that related to nested quantifiers. Example, determine the true value of each statement. Justify your answer by giving example or counter example. For question A, all x is belong to z integer, some y is belong to R, real number. 2x plus 3y equal to 4. For this question, we need to rewrite the equation. 2x plus 3y equal to 4, and we need to make y as a subject. 3y equal to 4 minus 2x, and y equal to 4 minus 2x divided by 3. So let x with any numbers of integer. So we let x equal to -1, and we substitute value of x equal to -1 into equation of y. So y equal to 4 minus 2 times -1 divided by 3, and we will get y equal to 6. Y equal to 6 is belong to R, real number. So this number is satisfied the question given, so the statement is true. For question B, all x is belong to R, some y is belong to Z. X plus y equal to 8. We need to let y as a subject, so we can suppose to take any numbers of x to exit the value of y. X plus y equal to 8, y equal to 8 minus x. So let x equal to 0.5, y equal to 8 minus 0.5, so we will get y equal to 7.5. However, y equal to 7.5 is not belong to Z. Since not all y give a true value, so the statement is false. Question C, some x is belong to Z, some y is belong to Z. 2x plus y equal to 7 and 2x minus y equal to 1. Since there are two equations given, so we need to solve simultaneously. We need to find first equation and second equation. So the first equation, 2x plus y equal to 7, we need to let y as a subject. So y equal to 7 minus 2x. So this is the first equation. For the second equation, we rewrite the 2x minus 1 equal to 1. We substitute equation 1 into equation 2. 2x minus y equal to 7 minus 2x equal to 1. So we will get for x equal to 8 and x equal to 2. X equal to 2 is belong to Z. So there exists the question given. Then we need to find the value of y. Substitute x equal to 2 into equation 1. So y equal to 7 minus 2 times 2, and we will get y equal to 3. Y equal to 3 is belong to Z. Since every x and y give a true value, so the statement is true. Question D, some p is belong to R, all x is belong to R. P squared plus q squared is equal to 0. As we can see, we can assume p and q must be 0 to make the equation equal to 0. If we let p equal to 0 and q equal to 1, 0 squared plus 1 squared is not equal to 0. The only value that p and q can have are 0 to make sure the statement is true. Not only some numbers of p, but not all numbers of q can exist in this equation. So the statement is false.
Hello, my name is Nur Izzatul Najwa, and I will continue the presentation about negating statements with quantifiers. Sentences that contain universal quantifiers such as all, every, each, or existential quantifiers such as some, there exist, a few, need some thinking while we write their negations. Let's continue to the example. For question 1, write the negations of the following statements. 1a, all new show will be displayed at cinema. To negate this statement, we will replace the underlined words with the opposite meaning of universal quantifiers, so that the answer for all will change to some and will be will change to will not be. The full sentence with the change will be the negation statement for question A. Same goes to question B. We need to negate the universal quantifiers to the existential quantifiers, which is a few to all and are not sold to are sold, so that the answer is all of the desserts are sold at the bakery.
Next, we will go to question number 2. The statement in symbolic form said, for every natural number x, there exists integer y, such that x minus y is equal to 10. So, its negation is, there exists natural number x for integer y, such that x minus y is not equal to 10. B. Show the negation of the statement. So, the statement in symbolic form says, there exists natural number x such that mx implies nx. So firstly, we need to negate there exists natural number x. So it became for every natural number x. Then we change the implied symbol by using definition of implication. Next, we expand the not symbol by using the De Morgan's law. Lastly, by using the law of double negation, we get mx and not nx. 3. Consider the following open statements where the universal set of all fruits. This means that x is equal to fruits. Tx, x is a local fruit in this stall. Mx, x has started to rotate. A. Express the statement all of the fruit in this stall has started to rotate in symbolic form. So we get for all x such that Tx implies Mx.
Next, I will proceed to question 3b. The first step is we put the negation symbol to the whole statement and simplify the symbolic of implies. The negation for all will change to some. After that, we use the De Morgan's law to get not Tx and not Mx. For the last step, the answer will be some x, Tx and not Mx by using laws of double negation. The conclusion will be some of the fruit in this stall has not started to rotate.
To conclude, logic and proving are important when it comes to mathematical problem solving, as there are proofs that can be used to solve this problem. Moreover, we will be able to expand the range of things that we know when we can fully understand the definitions of each mathematics problem. From the previous question that we learned, we can understand how to solve problems involving logical arguments containing quantifier, nested quantifier, and negative statement with quantifier. As we know, there are two types of quantifier, which are existential quantifier and universal quantifier. There are also nested quantifier that involves more than one quantifier. Apart from that, the negation of universal quantifier is existential quantifier and vice versa. Last but not least, we can also apply the concept of quantifier in our daily life. For instance, there are 20 persons in a class and some of them are wearing spectacles and all of them are mathematics students.